In this video, I will be reviewing the June 2022 Chemistry Regents, and I'll be doing the multiple choice section in this video, 1 through 50. And if you need to move to a particular question, as opposed to watching the entire video, which could be fun, okay, all you need to do is go into the description section of the video and click on the time code for the question you want me to review. Understand, I will be reviewing the question as if you have no clue how to do it, okay? So don't get angry with the comments if I'm over-explaining it. All right, so let's be crazy and start in order with number 1. So number 1, which subatomic particles are matched with their charges? Understand, we have 3 subatomic particles that make up every single atom, right? Protons, neutrons, and electrons. And so in the first 5 questions or so in this multiple choice, they love to ask about the atomic structure part of the course. And so you need to know the parts of an atom. And so the basics are very simple. We've got protons that are positive in the nucleus. We have neutrons. Hello, they're neutral. They don't have any charge. They're also in the nucleus. The entire mass of the atoms in the nucleus. And then we've got electrons that are outside that are negative. Okay, and everything about chemistry is how the positive protons are attracted to these negative electrons, unlike charges attract. Okay, so now you've got to go through these choices and figure out what these particles are. Now you can have these memorized, or you can see that, oh, okay, I made a silly mistake. But there is a table to go to, and knowing where to go could be very helpful. So we're going to go to that in a second, but bottom line is the protons are positive. Neutrons, okay, are neutral, all right? So protons are positive, electrons are negative, and that would be number 2 is the right answer. But let's say you want some place to have a reference guide to if you get all crazy, okay? So let's go to table O. Now, I always say table O like table O. So this is table O in all of its glory. And a lot of people use table O as a table in nuclear chemistry, but you can use it in atomic structure. Now, a beta particle, I always have my kids cross this out and write an electron, right? It's an electron. Electrons are beta particles, so you can use this for atomic structure. So it's an electron. And the top number in these nuclear diagrams here is the mass number. So we can see the top number for an electron is a 0 because it really has insignificant mass, right? It's 2,000 times lighter than that of a proton or a neutron. And we can see the charge. The charge is the bottom number here, okay, is -1. Go find yourself a proton, and the bottom number is the charge number. That's +1. And if you needed to know the charge of a neutron, if you couldn't figure out that neutron means neutral, neutral means no charge, the bottom number is a charge, and there it is, a 0. So using this table, top number is mass, bottom number is charge, and a proton has a charge of 1 or +1, while electron has a charge of -1. Yeah, the mass numbers on top, kind of like if you're looking at the periodic table, and the bottom number is a great way to think about charge. And that is a real easy way to use this table. So you can say an electron, a beta particle, is -1 and a proton is +1 if you didn't know that. Back to the question. So protons are positive, electrons are negative based upon, hey, your understanding of chemistry, if you remember that, or table O is your friend here, okay? So again, choice 2 is your answer for number 1. Going on to number 2. Number 2, which conclusion directly resulted from the gold foil experiment? Hey, this is from Ernest Rutherford, okay? And in this experiment, Ernest Rutherford shot something called alpha particles. And what they are 2 protons, okay? And I'm drawing my circles kind of terribly here, and then 2 neutrons. All right, so it's a particle that has an atomic mass of 4, but it's +2 because of 2 protons. And so this is a very slow-moving and pretty big particle compared to other particles if you look in table O. But, in any case, this particle was shot through a very thin gold foil. Now, so you understand the experiment, because it could be, asked of you in different ways, I'm going to draw an atom thick piece of metal. And we should know that the nucleus, okay, is really a small, tiny piece of that. Now, these alpha particles, I'll shoot as a different color, like red. So these small alpha particles, okay, mostly went through. In fact, most of the time, they went through, unabated, right? Straight through. And only once in a while, very occasionally, one of these particles got close to the nucleus and deflected away. When they got close, they deflect away. But when they're not, they go right through. So most of these alpha particles went right through. And if they're going right through and they're not hitting anything or being, deflected away, that must mean that the atoms are mostly empty space, right? Why would they deflect? Well, the nucleus, now that we understand it, is positively charged because it's made of protons, right? It's also made of neutrons, but they don't have a charge. So it's the protons in the nucleus that if an alpha particle, which is, by the way, is +2, comes close, it will deflect away. Now, because most of them went straight through, that means that very few times did that alpha particle come in contact with this positive nucleus. I say nucleus, but what Ernest Rutherford discovered was the nucleus. And he discovered that the nucleus was a very small piece of the entire volume of the atom, right? And all of the mass was located in this nucleus, in this tiny piece. So he discovered the nucleus. And that particle was deflected by a high positive charge in a very small volume, the atomic nucleus. So the answer here is number 1 here, okay? Just going through the choices, atoms are hard individual spheres. This would be the Dalton model. John Dalton was the first to bring back the modern atomic theory from the Greeks, okay, specifically Democritus, who believed in a indivisible particle called atomos, but that's not what this is about. Electrons located in shells, that was Niels Bohr, who organized the atom with electrons going in circular orbits. And electrons having a small mass was probably something that, definitely J.J. Thomson, who discovered the electrons in the cathode ray experiment. Okay, so you need to know those things, but this was about the atom is mostly empty space and that the entire mass of the atom is very small compared to the rest of the atom, and that very massive small part of the atom is positively charged, because we knew the alpha particle was +2, so the nucleus must be positive if it deflected away when it occasionally got close. Number 2 is 1. On to number 3. So number 3. The bright line spectrum of an element is produced when an excited state electrons do what? All right, very, very important concept here, okay, which was built upon the Niels Bohr model of the atom. So we've got ourselves a nucleus, which we know is positive because of the protons. We certainly know that there's neutrons in there as well. But what Niels Bohr did, and this is really the model that we used when we first thought about how bright line spectrum, which, by the way, you should recognize is those bright lines of colors that are given off when we give energy to elements or compounds. It's bright line spectrum. There is a particular type of spectral footprint that's given for each element. What that means is every element, okay, has a unique set of lines of colors that are emitted, and they could be used to identify elements based upon their pattern. And that pattern of bright light that's given off is when electrons are moving back toward the nucleus. So if you don't understand that, let's talk about these shells, okay? So this would be one orbit that's closest to the nucleus, and let's have another orbit, okay, that's a little farther away, and we'll just keep it just 2. And let's change the color for an electron to be red here. And so I've got an electron here in the first shell. And we'll say it's ground state, which means it's going in order. Ground state means the electron's in its lowest energy position. Now, you should know that anytime you're closer to the nucleus or in your ground state, you have low energy. That's really important that you understand that's low energy. And having low energy means that you are stable. Stability is an important understanding in chemistry, physics, physical science in general. So we're stable, okay? So high stability here, okay? Now, electrons are in this position because they have a unique energy level. They can exist a certain distance based on an exact energy level. That's called quanta. Now, electrons are negative. We know that protons are positive, and we know they attract each other. Now, if an electron wants to make a leap and jump farther away into a new position of an exact energy, it's going to need to absorb energy. So this is an important concept. We're in a low energy position. If we want to move to a high energy position, that makes sense, we're going to need energy. So energy is absorbed for something to move from the low energy position into a high energy position. That's really important, okay? And we call an electron that now has absorbed energy and now has enough energy to overcome this attractive force and move farther away, we call that an excited electron. Think about when someone's excited, they have a lot of energy. Sometimes they may scare us if you have a very, very excited person next to you because they have a lot of energy and they might do something with it that may, oh my gosh, affect us. Now, so this electron moved to a position that was farther away. It pulled away, it needed. So this is a high energy position. And you need to know that electrons or electron shells that are farther from the nucleus, okay, have higher energy. So this higher energy position called an excited state is not going to last very long, okay? So what's going to happen, eventually it's going to jump back to its ground or lowest position of energy. And if it's moving from high energy to low, it's going to give off electromagnetic radiation in the form of light of a certain color, or it could be visible. For this course, it's going to be in the visible region. So it's going to give off light as energy, okay, as it jumps back to its ground state. It's going from high energy to low energy. And by the way, when you're high energy, you are unstable. Unstable means that you have a position that you're not going to be at for very long. People that are unstable could have high energy and they're going to do something with that energy. So in this case, electron has high energy and it's going to jump back. In order for it to go low energy, it's got to release, okay, this electromagnetic radiation we call light, okay? And the type of light it gives off depends upon the exact distance it's jumping back toward. Every single, okay, atom has unique energy levels. That's why every single unique atom has a unique bright line spectrum. Now, I'm only showing you going from the second shell to the first, but there's 7 major shells, right? 7 periods on the periodic table. So I need, if I'm giving off energy or bright light, okay, or bright lines in this case, I've got to release energy. And I'm moving to a lower energy state, okay? A lot of times these questions can say, are you moving closer to the nucleus or away? When we give off energy, we're going to go from a high energy position farther away, and we're going to move back toward the nucleus, right? Yeah, if this is the nucleus that's positive, I always put the positive here, and let's just put electron configuration 2-4. This would be electron configuration of carbon. There'd be 2 electrons in the first shell, and there'd be 4. I know I only wrote 1, but this would be the ground state configuration. Now, if I want to go excited state, okay, then maybe I go 1-5. What just happened? An electron gained energy and jumped to the second shell. I know this question wasn't about excited states. Well, they didn't mention it, but they didn't ask for configurations. You need to know about it in this area of the test. Okay, so very important. This would be an excited state configuration. Why? Because it absorbed energy to move away. Think about that. All right, so in any case, The answer to question 3 is that it would release energy and move to a lower position as it gives off that light. Number 4. Number 4. The elements in the periodic table of elements are arranged in order of increasing what? Okay? So you should know that the modern periodic table of the elements is moving in the order of its atomic number or proton number. H. Moseley found that. You may think it's mass number. Now, if you did pick this, okay, it's not a bad choice, but there are places where it doesn't go in order of mass. The original periodic table was made by the mass number because back in the 1850s and 60s when we built the first periodic tables, Dmitri Mendeleev, right? All right. He didn't have a proton number. He didn't know anything about that. So they had a rudimentary mass numbers. So mass numbers were the original way we did that, but the more modern way is the atomic number. Now, if you're not sure, let's go to the periodic table. So here we are at the periodic table. If you notice, atoms go in order of the atomic number. They give you an example of the atomic number for carbon. It's the biggest, baddest, boldest number on the periodic table because it's the number of protons. And this identifies the element. And they go exactly in that order. Okay? There's no ifs, ands, buts about it. The atomic masses seem to be increasing, but there's going to be places where it does not. Okay? So we can see that in a couple different places. But if you look at, let's say, nickel and cobalt, all right, cobalt is 58.9332 and atomic mass is 58.6. So here's an example where cobalt is a little bit heavier. And by the way, when they discovered the proton number, okay, they actually had to flip some of these, all right? All right, so in any case, it is the proton number or the atomic number. It goes in order. So number 4 is atomic number 2. Number 5. Atoms of which element in group 15 have the greatest electronegativity? All right, so electronegativity comes up in a big way. Remember, the first 5 questions are usually atomic structure into periodic table. So now we're into periodic table concepts. But you need to know electronegativity is attraction for electrons. Really important that you know that. And the attraction for electrons, it's really attractions for other elements' electrons, but you can just keep attraction for electrons. Now, why is that such an important concept? Because it's going to affect bonding, whether something is ionically bonded, or where you pull electrons away, or you share them, where the difference isn't as great. But you have to know. Now, group is a column, okay? And so what they're saying is, who is going to have the greatest electronegativity? Well, we can answer this 2 ways. We can use the trends. Trends are understanding how the periodic table is built. The periodic table is built basically about periodic properties that repeat. That's why they call it the periodic table. What properties are repeating? Well, when the valence electrons repeat, you have similar chemical properties. Now, in group 15, they all have the same number of valence electrons. All right? And if we go down group 15, if you don't know, from the periodic table, we have nitrogen, we have phosphorus, we have arsenic, and we have bismuth. So there is going down. And what do we know? Well, you should know by going down, you can have this memorized, but it's really not important that you memorize it. You should know going down, the atoms get bigger. And they get bigger because we're filling more electron shells, right? In the row for nitrogen, we're in row 2. That's called period 2. And that means we're putting electrons in the second shell. And phosphorus is in row 3 or period 3, which means we're putting its valence outermost electrons in the third shell. And as I have already done, okay, we've got ourselves a nucleus that's positive, and the shells become what? Farther away. So as you go to bismuth, it's a bigger atom than the other because it's got electrons that are farther away. You say, Mr. Grotsky, why does it care the atom's bigger? Well, bigger the atom, the harder it is for this nucleus to attract the outermost electrons. So the bigger the atom, the more loosely held electrons, and therefore your electronegativity drops as the nucleus gets bigger. So you can expect bismuth to have the lowest electronegativity. Now, if you didn't like anything I just said, you need to understand that electronegativity is listed in the most underutilized table, and that is table S. So you need to go to table S, and you can look up everyone's what? Electronegativity and not have to know the trends. But if you understand what I just said, that'll be helpful for so many other types of concepts coming up. But let's go to table S. And here we are with table S. And notice it gives you the name of the element with its symbol, the atomic number. It gives you the first ionization energy, electronegativity, that's what we're after, melting point, boiling point, density, and the size of the atom's radius. All those things are given to you. People get questions wrong because they don't know table S has this. So let's go find nitrogen. Okay, so nitrogen is electronegativity of 3. We'd expect it to be high because it has a very small radius. It tracks and pulls in its electrons. Now, under nitrogen, there's phosphorus. And if you don't know that, in group 15, you can see that in the big table. And notice its radius got bigger, which means its electronegativity decreases. Okay? And then if we keep going, we're going to come into arsenic. We're going to have to move on. Okay, and find arsenic, and it's atomic number 33. It's in the same column, and you could see that arsenic is 2.2. It didn't get really much lower, although its atomic radius is bigger, but it's a trend, right? So the trends aren't always perfect. And then bismuth, okay, let's go find that, Bi, and we're going to keep going till we find bismuth. And there it is, atomic 83. And its electronegativity is 1.9, lower than the 3 previously looked upon. So bismuth is 1.9, and by the way, it has the largest radius of all the 4. As you move down, the radius gets bigger, which means the attraction for electrons decreases electronegativity. So bismuth has the least attraction. That's why it is big. Those that are closer to the nucleus are attracted more. All right, so bismuth is the answer based on table S if you don't want to use the what? The trends. Okay, silly to get this one wrong. So number 5 is 2 in all of its glory. Okay, so number 6. Number 6. Which term represents the simplest whole number ratio? The simplest whole number ratio is the lowest ratio of a molecular formula, or we call it an empirical formula, the lowest whole number ratio. Okay, there really isn't any more to that, although I do see a lot of questions where let's say, hey, what is the empirical formula of a molecular formula? For a molecular formula like glucose, it would be C6H12O6. This is exactly the number and types of atoms in a molecule that's covalently bonded. But its lowest ratio would be CH2O. That would be its empirical formula, right? Atomic mass and formula mass have nothing to do, okay, with the ratio of atoms. The structural formula, we see a lot of this in organic chemistry, where like you see exactly the shape and how and where, more importantly, the atoms bond. So this is the ethane, right? So this is a structural formula. Structural formula may not be in its lowest ratio. Its ratio is how it exists in nature as a molecule, and that, of course, would be a molecular. But there are some formulas like structural molecular that are already in their lowest ratio. Water is a molecular compound. It's bonded covalently, and it exists as one oxygen bonded to 2 H's in this bent molecule that you may have learned, and it's a 2-to-1 ratio already, so it's already in its lowest ratio, okay? But it's also the molecular. They don't have molecular here, they've got structural. So empirical lowest ratio. And so therefore the choice of the answer here is number 3, empirical formula, okay? Number 7. Number 7, how many electrons are shared in a triple bond between 2 atoms? So if we've got a triple bond, we should understand that triple, double, these types of bonds are covalent bonds. You're not going to see this in an ionic or metallic. So right away, multiple bonds, okay, or something where we deal with sharing of electrons. And we should know that a bond is a pair of electrons, right? If we were to do the Lewis dot diagram of hydrochloric acid, hydrogen has 1 valence electron, chlorine has 7, and 2, 3, 4, 5, 6, and 7. So chlorine started with 7, and by sharing 1, it feels like it has 8, hydrogen sharing 2. And there's 1 bond here. And that 1 bond, okay, is right here, and it's a pair. And you could also draw it like this. An H with a single bond to a chlorine. You must always put the lone pairs, right? There are 3 lone pairs. So a dash is a single bond. So if you got 3 bonds, you would have 3 pairs. The greatest example of that would be the diatomic molecule of nitrogen. Nitrogen has 5 valence electrons. 1, 2, 3, 4, and 5. Another nitrogen also has 5 valence electrons. 1, 2, 3, 4, and 5. And so when we do Lewis dot diagrams, a lot of times I'll tell my students evaluate by sharing this nitrogen feels like it has what? 8. And by sharing this one feels like it has 8. But they are sharing a total of 6 electrons. And a pair is a bond, so that would be a triple bond, right? So nitrogen would have 3 bonds. And if we're drawing Lewis dot diagrams, I need to show my lone pair. So the total number of electrons would be 6. Number 7 is choice 1, number 6. On to number 8. Number 8, given the equation representing a reaction, what occurs during this? Classic Regents chemistry question. We've got a chlorine particle of 2 chlorines, and it's bonded, and now it's breaking apart into 2 chlorine atoms. So we've got a particle of 2 chlorines breaking apart, okay, into 2. So if you think about it, 2 little circles, right? They're bonded, and now they're going to make individual atoms. So clearly, what keeps 2 atoms together is a bond. So you need to understand that a bond has been broken. All right, so we got choice 1 or choice 3, right? Now, if we draw chlorine, and I left these Lewis dot diagrams up here, let's do this. Chlorine has 7 valence electrons, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here comes 7. And another chlorine has 7. 1, 2, 3, 4, 5, 6, and 7. You can see that chlorine, by sharing a pair, which is 1 bond from number 7, it is very stable. All right. And by the way, the dots are the valence electrons. Chlorine is 2-8-7. The outermost is the dots, always. It's the valence. But, okay, in order for us to go from this particle here, Cl2, to individual atoms, we've got to break this bond. Okay. Now the question becomes, are we going to add energy, or is energy going to be absorbed in breaking bonds? And the way to understand this is to understand that bonding is a stable state. We've heard this word before if you've been watching many of my videos or other questions. Stable is low energy. You need to understand that the reason why atoms bond, the reason why 2 chlorines come together and bond, is to achieve a low energy position. Okay? Thermodynamics, the flow of energy, goes from high energy to low. That's one of the driving factors in how things work, okay, in physical chemistry. So, we notice that 7 electrons is not filled. We want what we call an octet rule. So again, as I said before, the reason why these two chlorines bond is they both feel like they are sharing now 8. When they were individual, they had 7 valence electrons. But by sharing that pair, or 1 of each, they both feel like they have 8. And 8 is like a noble gas. 8 electrons beyond the first shell is a very low energy position. So atoms are using each other's electrons to achieve the octet, the 8, the low energy position. That's really important to understand this. Why? Well, I've got a low energy position. And now there are going to be individual atoms that don't have the octet. That's going to be high energy. How do I go from low to high? I must have to absorb energy. Energy is always absorbed to break bonds. 8 is 3. Think about it. If I want to go break something, I need energy, right? Now, they love to flip this on its head. If I did this reaction the other way, where I had chlorine atoms who had 7 valence electrons, and they come together to make Cl2, then we're going to know that we're going to make high energy going to low energy. And anytime we go from high to low, energy is released. Hey, making a bond is a low energy position. How do we get low? We've got to release our high energy. You've seen this before in your course. Okay, if you do a heating curve, solids are low, phase change, liquids are higher, gases are higher. To go from a solid to a liquid to a gas, you're going to need energy. Climbing the ladder requires energy, endothermic. Going down is exothermic. So for all those reasons, 8 is number 3. Number 9, krypton atoms in the ground state. That means where the electrons are originally in their lowest position. They're not jumping away, right? They're in their lowest energy position. Got to fill 2 electrons fills the first shell before you put 8 in the second. So they're going in order. Tend not to bond with other atoms. So they're talking about krypton atoms in the ground state do not tend not to bond with other atoms. You should understand that krypton, which is Kr, and if you needed to find that out, you can go to table S, is a noble gas. Or they call this an inert gas, right? The noble gases are a family of elements that are group 18, and that column or family means that they're related by the fact they all have 8 valence electrons, okay, with the exception of helium, which has 2, which fills its first shell. So what's so special about noble gases? Well, they have what? Stable, which means low energy, stable, low energy electron configurations, which means their outermost shells usually are filled or have the 8 electrons, or the octet rule has been satisfied. Okay? So, what are we talking about? Well, when we talk about bonding, we're talking about the outermost electrons. The innermost electrons, called the kernel, these electrons are not available for bonding because they're held more tightly, okay, to the nucleus. Sometimes we call them the core, like in other courses. The core electrons are extremely stable, which means they're so close to the nucleus, they can't move much. You take so much energy to mess with them. But the outermost electrons, right? The outermost electrons that are in shells that are farther away, feel the nucleus less. The outermost electrons, they have enough energy. These are the higher energy electrons because they don't feel the nucleus as well. They have the energy to share electrons or transfer and that types of bonding. But bonding is with the outermost. The innermost electrons are not part of bonding. These would be the kernel electrons, right? These kernel electrons are too stable, okay? They don't have the energy to be lost or gained. You would need so much energy to pull them out of those positions. This has the energy to be involved in bonding, either being transferred or shared. Okay, transferred, of course, ionic, shared, covalent, really important. But what's so special about noble gases is they don't partake in any bonding because their shells are already filled, or their outermost shell has that 2, or in this case, the 8, right? And so everything wants to have that octet. I was drawing chlorine in other problems. The Lewis dot diagram for chlorine bonded to itself. Let's do it one more time. Okay, now chlorine has 7 valence electrons. It's a halogen, They're related by all the column having 7. Another chlorine would have 7. And so when I put them together, you can see by sharing, okay, this chlorine feels like it has 8 now. And that's why it bonds. It started with 7 valence and now it has 8. So the reasoning that things bond is to achieve the octet. By the way, chlorine becomes -1 by gaining 1 more electron. Its outermost is 7. So the driving force why things do what they do is to achieve a low energy electron stable configuration. So my friends, the answer, or my enemies if you hate this, it's the outermost. So it's the outermost shell contains 8 electrons. And if you weren't sure about that, let's go to the periodic table. So if we go to the periodic table, we see our xenon and krypton, all right? We can see that the outermost of all of our noble gases here are 8. Exception would be helium because it only has 2 electrons and they fill the second. So the outermost, I don't care if this question was xenon, krypton, argon, and neon, because they're in the same column. They have the same valence electrons. They have the same chemical property. In this case, the noble gases, their chemical property is their inability to have a chemical reaction. Okay? So in any case, it's the outermost with the 8. So 9 is 4. On to number 10. Number 10. All matter can be classified as, well, looking at the choices, an element's not going to work because not all matter are made up of just elements. Elements are the group of the same type of atoms. For instance, copper has its own symbol, capital letter there. But you notice that there are a lot of things that are compounds where there are 2 or more different elements or 2 or more different capital letters bonded, so they could be compounds. So we can be elements, we could be compounds, but then we can have more. We can have a mixture of these things. So to really understand this problem, we need to break down how matter is classified. So we have heterogeneous matter, and then we have homogeneous matter. Okay, now matter can be broken down into these 2 types. The same throughout is homogeneous, or heterogeneous is different throughout. Now, there can be homogeneous matter that can become a substance. That comes up a lot in this course. A substance. That's important. It's made of just one type of piece of matter. Now, a substance can either be an element. We just mentioned that. What that just means is it's made up of a group of the same type of atoms denoted by the same number of protons. So if we have the element symbol copper, okay, they are all the same type of atoms with the same number of electrons. Protons, right? They can have the same number of electrons because electrons equal protons, but proton, I want you to know, is the atomic number that identifies the element. Now, if they're a group of different elements bonded in an exact ratio, we call that a compound. Okay, if you think about sodium chloride, it's a 1-to-1 ratio of sodium to chlorine. Notice there's 2 different capital letters denoted by 2 different atoms bonded in a 1-to-1 ratio. We know water is a compound. There are 2 hydrogen atoms for every 1 oxygen atom that's bonded together. This formula never changes for water. Okay, it's not sometimes H3O. So things about compounds is there are 2 or more different, okay, elements, which means 2 or more different atoms, okay, 2 or more different symbols or capital letters, bonded in an exact ratio. Water is always 2 hydrogen atoms per 1 oxygen. And so that is a substance. It's either an element, which is a group of the same type of atoms, or a compound, a group of the same type of molecule, okay, or formula. I say formula because things that are ionic, like sodium chloride, metal, nonmetal, have a formula, which is the lowest ratio, okay, formula, in a crystal, right? It's important. This is covalent. It makes molecules, okay? Any case, both of these are homogeneous because water is always H2O particles. Copper is always Cu particles, or particles with 29 protons. Any case. Now, we also have mixtures, okay? Now, there's homogeneous mixtures. Now, a mixture is not a substance. This is important, even though we haven't seen it. A mixture is made up of substances, right? There's different things that are close together, not bonded, and they retain their individual properties. So substances, okay, I should undo that right there, and I'll add substance is, okay, which means they could be different elements, different compounds in close proximity, but not bonded. They're made physically. A homogeneous mixture, by definition, is a solution. And a solution is denoted by something dissolved, a solute, into a solvent. For instance, if I write NaCl aqueous, that's a solution. Or sodium chloride has been dissolved in water. The aqueous, AQ, means that I've been dissolved in water. And so we have water is a compound, and it's mixed with sodium chloride, another compound. It's a mixture of substances. Okay? Now, if it's a homogeneous mixture, like we have off here, it's a definite solution. And this could be air, because gases will mix together evenly, or things that dissolve. Now, if they don't dissolve, they're going to make a heterogeneous mixture. Right? That would be like sand and water. You have a lot of water, then the sand. They're not evenly mixed. Things that don't dissolve in each other won't be homogeneous. So heterogeneous mixture would be like, rocks on a beach, pits in a watermelon, okay? Or chemically, you'd have a precipitate, which is a solid, okay? And you'd have a solution above it. So you'd have solution and some solid, okay? So heterogeneous mixture will also have substances, but they won't be evenly mixed. All right, so back to the question. All matter can be classified as a compound. No, it could be an element too, but the best answer is 4. It can be a mixture, and that could be of elements, compounds, or it can be a substance. See, a substance could be either what? An element or a compound. So we're either going to be a mixture, which is going to have more than one type of substance, okay, many substances or one substance. So a mixture or a substance covers all of the matter, all right? And so 4 is the best answer. Either a mixture of elements and compounds or some combination, all right, or one of these two things, all right? And so choice 4 is the best answer for number 10. On to number 11. Number 11, which sample at standard temperature and pressure has the same chemical properties as 10 grams of aluminum at STP? So we're not changing the temperature, the pressure, but they want the same chemical properties. Normally questions like this, they'll be similar. And when you hear similar, you think about elements being in the same column or that same family of elements because they have the same valence electrons. But this is just the same. So if I look at my choices, I see I have aluminum solid. And so that's my choice. Interesting enough, they have 10 grams, so they try to kind of fool you with the amount of grams. And whether I have 5 grams or 10 grams, understand that grams is an extensive property. It's based upon the size of the sample. We can't really identify anything based upon grams. So having more or less mass doesn't change any of the properties of aluminum, and you can't identify anything. So the mass is inconsequential. Now, of course, if you take that mass and divide it by volume, you get density. Density is an intensive physical property we can use to identify. So I always think of intensive physical properties if that word comes up. Intensive are talking about those properties you use to identify, like melting point, boiling point, solubility, density, color, right? Extensive properties are based on the size of the sample. and so is mass. So mass has nothing to do with identifying something, just mass alone. So they want the same chemical properties as aluminum would be, well, aluminum. Again, a kind of a silly question. I guess they're trying to get you with a different amount of grams, which you can't identify things with. So 11 is clearly going to be 3 here. So in any case, on to number 12. Number 12. Which sample of matter cannot be broken down by a chemical change? A chemical change is breaking bonds or making new ones. It's all about creating a new substance by rearranging the atoms. So we either break bonds, okay, or we make new ones. Break old ones, make new bonds. And that always leads to a new substance. A substance is either a compound, all right, or free elements. So you make a new chemical formula. All right, so anytime a new chemical formula appears, it's a chemical change. Now, if we look at these choices, which one cannot be broken down? Which one can you not break the bonds? Well, if you think about it, ethanol, which you should know from organic chemistry, is 2 C's, and that OL is an alcohol. It's bonded to an OH. Okay, and you fill in the rest with the carbons. Now you have to do all this for the problem, but I'm kind of over teaching it here. You can see that there's bonds between the carbons. There's bonds between the O and the H. Remember, these dashes are H's, so there's bonds everywhere to be broken. Okay, so you can pull the hydrogen away from the carbon by breaking bonds. That'd be chemical, so it can't be 2 because we're looking for something that cannot be done. Methane. Okay, well, methane, I'll draw that, down here. Methane, of course, is this compound where you have 4 bonds. Remember, carbon always has 4 bonds because it's 4 valence electrons, and it's going to be methane. It's saturated, single bonds between the carbons. In this case, there's no other carbon. So you can break what? 4 bonds here. This is another compound. Compounds are 2 or more different elements with an exact ratio. They're bonded. So that can't be. And we know water is also a compound. It's, of course, oxygen bonded to hydrogens. It's that bent molecule, that polar molecule. It's got 2 lone pairs. If we're drawing a Lewis dot diagram, we should draw them. But there's obviously 2 HO bonds that can be broken. So what they gave you was 3 compounds. Compounds have what? 2 or more different atoms. So party people, okay, if we look at this, antimony, if we're not sure, okay, is an element. All right? And if you look at antimony on the periodic table, or I should say table S, you'll find that it has its own chemical symbol. This is an element. And elements cannot be broken down to anything simpler. So if you notice, this does not have anything it's bonded to. So there's no bonds to break, so there's no chemical change that can happen. I see this question in complete opposite, where they say, which of the following can be broken down? And guess what they give you? They give you 3 elements. If you're not sure if a name is an element, go look it up, okay, on table S. They give you the atomic number, the chemical symbol, and the name, all right? So these 3 here, okay, are compounds. This is an element, has its own chemical symbol. Table S is your friend there. Now, again, if I flip this on its head and have 3 elements and 1 compound, then hey, then I know that's which one can be broken down. And that, of course, is the 1 compound. Don't forget, they love to ask, they seem to always add ammonia. And people say, what the heck is ammonia? That's NH3, and that's listed in table K as NH3 is another compound that pops up in this course. The rest of these compounds you should know from experience, like water or your organic chemistry unit. So in any case, the answer is 1 for number 12. On to number 13. Number 13, based on table F. Okay, well, we should go there, right? It's telling you. Which 10-gram sample, when thoroughly mixed with 1 liter of water at room temperature, forms a heterogeneous mixture? Okay. Well, we should know a heterogeneous mixture is a mixture of substances, 2 or more substances, an element, compound, 2 compounds, that is not evenly mixed. The greatest example of a heterogeneous mixture in chemistry is when we have undissolved solute particles. Okay, now we can also call that a precipitate, right? A precipitate is a compound that's not soluble, okay, or there's some stuff undissolved. So when I think about table F, okay, if it's undissolved or precipitate, that means that these things right here are insoluble, right? So there's stuff that's undissolved or there's a precipitate. Bottom line is, okay, so based on table F, they're asking for which one forms a heterogeneous mixture, which means in chemistry, if we have a beaker, we're going to have, let's say, some water, and then we're going to have some solid that doesn't dissolve. And if it doesn't dissolve very well, it is insoluble. And in table F, okay, we can know which salts are soluble or insoluble. All right. So if I look at my choices 1, 2, 3, and 4, okay, which is ammonia chloride, Ki, AgBr, or sodium nitrate, I can go to table I and I can decide, based on that table, who's soluble. Let's go there. So table F is here we are, and when we look at this, we can see that there's the solubility guidelines, and we have soluble and insoluble compounds. The first compound was NH4, okay, Cl, ammonium chloride. And if you notice, we have the ammonium ion right here. And if you have the ammonium ion, you make a soluble compound, which means you dissolve. You're not going to make a heterogeneous, you make it a homogeneous. Homogeneous is you make a solution because you are soluble. There are no exceptions, okay? So that one is very soluble, okay? Now the next one is potassium iodide. I'm writing it here because potassium iodide is Ki, that's what they give you. And you know, potassium is a group 1 ion. Group 1 means that you're in the first column. They give you lithium, sodium, and etc. But if you go down the column 1, it's called the alkali metals, you've got lithium, you've got sodium, you've got potassium, cesium, rubidium, keeps going. So K is in that first column, that group 1. So no exceptions. If you have any one of those ions, you're soluble. So Ki is also soluble, which would make a solution which is homogeneous. The first drop is the same as the last because it equally dissolves. Okay, and the next one is AgBr. Okay, so AgBr, silver bromide, these are all salts, by the way, ionic compounds. We know that Br is soluble. It's right under the soluble column. Now there are some exceptions, right? And so the exception is when it hooks up or it bonds with silver. I know that's an exception because it's written in the compound. So normally bromide or Br negative ions, when it bonds to things, are soluble, except in 3 cases, and this is one of them. So AgBr is not soluble. We would not write aqueous. So the ones that are soluble, I should have put aqueous here. They make homogeneous solutions. They will dissolve, okay, very equally. But AgBr will not dissolve. It'll be a precipitate. And that's what's going to make a heterogeneous mixture where you're going to have a lot of the solid on the bottom and then a lot of the water solution above it, okay? But just for fun, if we keep going, because it is fun, sodium nitrate, NaNO3, is the other compound that's given to you, choice 4, okay? And notice sodium is a group 1 ion, so that's soluble with no exceptions by itself. And nitrate is that negative ion here. If you don't know, NO3 is -1. Table E above this one tells you that. But if you have either one of these, it'd be soluble. You have both. So this, of course, is very soluble. And the nitrate alone makes it soluble, and the group 1 ion. So this would have an aqueous too. So the only one that would not dissolve and not be evenly mixed, okay, would be silver bromide, okay, the insoluble compound. Going back to the question. So number 13, the only one that's not soluble is choice 3. So 13 is 3. Now, if you had no idea what any of this meant, you could have went to table F and you could have saw which one was different. Okay, this is soluble, this is soluble, this is soluble, this wasn't. That had to be your answer if you didn't understand what that meant. So again, in the multiple choice scenario, you can eliminate or find your answer sometimes by seeing what's different from the rest. So 13 is 3. Number 14. So number 14, compared to a 1 molar sodium chloride aqueous solution, that's NaCl dissolved, okay, in water at 1 atmosphere, a 2 molar solution at the same pressure has what? Well, if you've got more solute particles, the solute particle is the NaCl, dissolved in water, okay? So careful reading, compared to the 1 molar solution, hey, a 2 molar solution with more stuff is going to have more solute particles dissolved in the water. And the more solute particles that are in the water, the more it gets in the way of the water trying to either boil or freeze. It's going to make it harder for the water to boil or freeze. So you're going to need a higher temperature to boil, and you're going to need a lower temperature to freeze. So the boiling point is always going to be elevated for a solution compared to the pure water, and it's always going to be lower for the freezing point. Now, both of these are solutions, but the more particles that are dissolved, the higher the molarity, the lower the freezing and higher the boiling point. Okay? So it makes it harder to boil, so you need a higher temperature, harder to freeze, so you need a lower temperature, and that's why these arrows go opposite. I have a way to remember this. I don't know if I can draw this, but if I do thumbs up for one hand, I think I'm missing some fingers here, and I do thumbs up, this is going to be challenging for me, and thumbs down, oh, that's ugly, going downward, okay, and I always know that the up thumb goes up and the down thumb goes down. I always say that's the secret symbol to get into the chemistry party. And so take your two fists and have the thumbs going opposite of each other. And as you add more stuff, the higher what? Boiling point is elevated and the lower freezing point goes down, right? Boiling's higher than freezing. In any case, the boiling point, okay, is going to be elevated because it's harder for it to boil, and the freezing point is lower because it's harder to lower. And this comes up a lot, all right? So 14 is 3, all right? On to number 15. Number 15, which list includes 3 forms of energy? Well, the first thing that jumps at me is the temperature. I know a lot of people think, oh, temperature is the average kinetic energy. Actually, that's not true. Temperature is proportionate to, okay, the kinetic energy. We read a line above to say average, meaning as temperature goes up, the kinetic energy proportionality or proportionately increases. You go faster. Kinetic energy is motion. So as temperature goes up in a system, the particles are moving more. But temperature doesn't measure energy, right? If you know that your thermal equations that you use, Q equals mc change in T, temperature is part of it, right? How much motion generally we have, but you need a specific heat, and you need to know, hey, how much of it to actually measure the Q, right? So that's how it works. Temperature gives you an indication, but it's not a measure of energy by itself, right? That's important. So we can eliminate 1 and 2, and I know a lot of people, okay, fell for that on this test. So any case, so that's gone there. So now we're down to 3 and 4. Now, by the way, chemical is a form of energy for sure. Chemical energy is an example of certainly all types of chemical reactions, okay? It's really the energy in the bonds, right? So if we give off heat in a chemical reaction, it's the change of the energy that was in the bonds in the reactants to the energy in the bonds of the product. So chemical changes give off or absorb energy because of the chemical bonds have a unique type of energy. Thermal is, of course, heat, motion, right? So thermal energy. So these two are good, but the temperatures. And alkalinity is a measure of, pH, okay? Or in this case, basicity. It's a fancy word for basic, okay, or basic property. So that's not an energy one. That's why 1 and 2 are gone. All right, so we can know that alkalinity is not a measure of energy, as we just said. It's a measure of basicity. And you think of alkaline earth metals, right? That's the column 2 metals like beryllium and magnesium and calcium, right? Those are all make, well, at least some of them make strong bases, and that's why you hear the word there. So that's gone. So it's going to be 3, and if you're not familiar, electromagnetic energy is a radiant form of energy, we think of it as light, or all things that are like light that have wavelengths, right? They travel in waves, right? That electromagnetic spectrum you learn from like X-rays all the way to radio waves, which are safer, and then the middle part is the light. So that's a type of energy, and you should be aware of that one for sure, because that's what's given off when electrons jump back to their nucleus and give off bright line spectrum. So electromagnetic is a type of energy, okay, that makes the bright line spectrum. Hey, nuclear energy, this is the energy changes in the nucleus. That's why, and they by far are greater than any chemical changes in chemical bonds, right? So when you make a nucleus more stable, okay, certainly the changes there are tremendous, okay? And of course, you talked about chemical energy. So because of all of that, okay, 15 is choice 3. But the biggest misnomer is that, hey, temperature is average. No, it's proportionate to. It's not temperature exactly. In any case, 15 is 3. On to 16. Number 16 is a classic Regents question. Under which conditions of pressure and temperature is a real gas most like an ideal gas? So I kind of use this analogy that an ideal gas is like an ideal student. Comes to class early, leaves late to ask questions. The only way to do that is it has to be fast. The only way for it to be fast is it has to be very, very light and has very little volume, insignificant volume. I'm not trying to make any type of, descriptors of anybody here. Right? And it moves in straight line motions because it wants to get to where it's going. It's very random and independent. It doesn't really attract people very well. There's absolutely no attraction to people. So it doesn't go see its friends. It doesn't have any friends. It goes straight to class, moves in a straight line. And when it bounces into people, because sometimes people are in its way, it bounces directly off and then goes back to class. It doesn't say, I'm sorry. It doesn't stick with the people. We say that kind of collision is elastic. Okay, those are ways to think about the ideal student, which, by the way, doesn't truly exist. So if I'm offending anyone, I'm not. Okay, a real student really likes people. They're social animals. They're attracted to each other. So when you think about that, they move slower. So gases that are real really have attractions for each other. They move in curved paths. Ideal gases are far away from each other, and they're moving independently. They're not caring about each other. There's no attractions at all. Okay, so how can I make, all right, a real gas that really has attractions become a gas that has none? Well, the first thing I'm going to do is I'm going to lower the pressure. Right? If I lower the pressure on them, right? You think about pressure, think of a force pushing these together. Okay? So if I lower the pressure, okay, on them, these molecules will go farther apart. And if I make them go faster, and we just learned from another question that temperature is proportionate, okay, to the average kinetic energy. So if I increase the temperature and I make them go faster, they have less chance of attracting. So it's low pressure, high temperature based on those understanding. But there's an easy way to remember this. If you're here to get the easiest question, you can use the word plight. I see it used all the time, so I'm going to break down and I'm going to use it. So plight here, all right? And you think of ideal gas. What do they have? They're going to have low pressure and high temperature. Okay, so if that works for you, fine. I'd rather you understand what I just hear, but plight will do it. 16 is 2. On to number 17. Number 17. Which sample of argon gas has the same number of atoms or particles as 100 milliliter sample of helium gas that also is going to be made up of just atoms at the same at 1 atmosphere and 300 Kelvin? So we have 100 milliliter sample. And it's at 1 atmosphere and 300 Kelvin. Which of the following choices will have the same number of particles, or in this case, atoms? I call this the same problem. Okay, and it's based upon Amadeo Avogadro's hypothesis. Okay, Avogadro's hypothesis stated if you have two volumes that are equal for two different gases, if they're both under the same conditions of temperature and pressure, if they're the same volume, they'll have the same number of particles. So all you need to know is, I'm looking for the same volume as long as what? We have the same pressure and temperature that was given. And so that's all you need. And you kind of know this because you learned in your chemistry course that if I have 1 mole of any gas at STP, it occupies, if it's an ideal gas, 22.4 liters. Okay, well, 1 mole represents a certain number of particles, right? So if I have 2 gases that both occupy, right, 2 separate gases in 2 different containers, but those containers are both 22.4 liters, and they're both at the same STP, they'll have the same number. Of course they do, because 1 mole is equal to 22.4 liters of any gas, as long as it's at the same temperature and pressure, in this case, STP. So you kind of learned that already. So same volume, same temperature, pressure, same number of particles. They just used atoms. And careful here, the reason why they used atoms and not molecules is helium is a noble gas. It doesn't bond, so it's just helium atoms as a particle. Okay, and argon, also a noble gas, which is the last column, they're very stable, they don't bond, is also an individual atom. These gases fly around, they don't bond, so they're just atoms. Avogadro defined a molecule as a single particle of atoms or particles of atoms bonded to each other. So like water vapor is still 1 particle. So in any case, it's the same problem, and same volume, same temperature, same volume, same temperature and pressure, same number of particles. In this case, it was atom. Number 17 is clearly 4. On to number 18. Number 18, which process is a chemical change? A chemical change is when we're going to make a brand new compound or substance is going to appear from a compound. We're going to break bonds and reform new ones. So we're looking for a chemical change. What's not a chemical change is a phase change. So if you notice, condensation just means that a gas of H2O is going to become H2O liquid. Notice the chemical formula will not change in condensation. Look at choice 3, evaporation. That means a liquid of this chemical will become a gas, but it'll still be C2H5OH, but its phase will be a gas. Notice we're changing the phase, but we're not changing the chemical formula. What we're doing is changing the space between them by overcoming attractive forces. And sublimation, you should know that sublimation is when we go directly from a solid, you need to know this, to a gas. But notice it's also a phase change, right? Solid to gas just means that the molecules, the particles, are separated. We overcame the attractive forces. So the chemical formulas do not change. So therefore, 1, 3, and 4 are phase changes. And changing a phase is physical. You're not breaking bonds. It's important you know that. That's what this question's about. The synthesis of MgO means what? Well, if I write down here, magnesium atoms plus oxygen atoms, except oxygen atoms are going to be O2 because they're diatomic, will make MgO. Now I need to balance this, right, because there's 2 O's here, but I put a 2 here and 2 magnesiums. Bottom line is 2 different elements make a compound. Okay, we break the bond here and make brand new organization of atoms with a different formula. That's a chemical change. So 18 is 2. On to number 19. Number 19. Which property is determined by the structure, arrangement, and interactions of the molecules of a substance, that could be an element or a compound, at a given temperature and pressure? Well, this is an odd question. I haven't seen one like it, but if I go through my choices, atomic radius is the distance from the nucleus, which is positive for the protons, and the outermost electrons. that doesn't really talk about the arrangement of molecules. It talks about the arrangement of electrons and how far they are in an atom, so that's not going to work. Half-life is the time it takes for an unstable nucleus of a radioactive atom to become stable and half of its original compound transmutate or decay into something more stable. And that's, we're not dealing with the nuclear changes here. Okay, we're just trying to describe matter. Formula mass is certainly the amount of grams a compound or an element, well, really a compound if we say formula, right? That would need to equal 1 mole. And so by a process of elimination, you're left with physical state, because those are just 3 bad choices. And when I think of physical state of matter, that's the way that I usually use this. Okay, matter, I'm running out of space there. But I think about solids, liquids, I guess I'll just use the abbreviation, and gases. And the arrangement, well, solids have a 3-dimensional repeating structure called a crystal. Liquids, okay, don't have an organized arrangement, but they don't always fill the container. And gases always fill, and they have the greatest distance and, of course, the greatest kinetic energy and the least amount of attractive forces. Solids have the most. And that's what these interactions mean. So they're just really talking about solids, liquids, and gas phases and how they differ. But if you couldn't sniff that out, okay, so to speak, then obviously these 3 choices are so bad, okay? But I haven't seen a question like that. But they're talking about the physical states of matter, solid, liquid, and gases, and that's what these 3 things are discussing. On to number 20. Number 20, a collision between reactant particles is most likely to result in a reaction when particles have proper orientation and proper energy. Hey, this defines what we call as an effective collision. And sometimes they'll bring this up. An effective collision, okay, is a collision that leads to either breaking bonds or forming new ones. Effective collisions are those collisions between atoms or molecules that lead to a chemical reaction, a chemical change. A chemical change is making something new, a new arrangement, a new formula, which means you have to either break bonds and or form new ones. Okay, so that's what that's about. So that's just a straight definition of effective collision. The rest of these really don't make any sense. Okay, and the orientation part, if that gets you, now let's talk about the proper energy. That proper energy, if you don't recognize, really is the activation energy, right? If I have a potential energy diagram and we have this amount of potential energy, to get to the top of the hill, which is the activated complex here, if I draw this complete, right? So if I keep going here, so this is the activated complex energy, if I can draw a straight line. This is the activation energy. It's the energy I need to get to the top. Once I get to the top, the reaction will go. So really, this proper energy that you need is really the activation energy to overcome this reaction barrier. Okay, but in any case, and of course the orientation is that molecules have places where bonds can occur and places where they can't. And that's important. Just because it collides with enough energy doesn't mean a reaction will go. All right, and that's what that means. And you probably learned this a little bit in biology, but you know, if we talk about a reaction in organic chemistry, you have to know, which is called an addition reaction. Well, an addition reaction is when we have something like Cl2. It has to collide with these double bonds right here for both chlorines to break the double bond. And for, well, essentially, we have to tack that area for both chlorines to add on completely. We call it addition because once you lose that double bond, you have room to add 2 chlorines, and 1 would go on each carbon. So the collision has to occur there. If that collision occurs where there's hydrogens here, no matter if you have enough activation energy or not, it's not going to cause a bond to occur. It's got to collide in a certain area. That's the proper orientation, right? So in any case, 20 is choice 2. On to 21. So number 21, given the equation representing a system at equilibrium, and of course the double arrow is a big hint that we're in equilibrium. Which statement describes a reaction? Okay, so this classic Regents question. So if we're at equilibrium, the best way that I can think about equilibrium is, let's say I have 3 people on this line, on this area of the room. And let's just say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. So 3 people on this line and 10 people. And I asked the people, of course, they're being nice in doing this for me, to switch lines evenly, which means one person will move to this line as fast as one person moves to this line. And if I ask one person to switch lines every minute and I come back in an hour, you can guess that the number of people on each line is staying the same. All right? So it's important to recognize if you're in equilibrium, and this represents the reactants, and these are the products, if the rate of the forward equals the rate of the reverse, rate means speed, and I was asking each people to switch lines at the same rate once every minute, the amount of each of the reactants and products should stay constant. And that's why choice 2, okay, is correct. People, when they get this wrong, they think that equilibrium means the amount of reactants, or in this case people, will be equal. No. Okay, very rarely do the lines are ever equal. So it's when the rate of the forward equals the rate of the reverse. So as fast as NO2 becomes N2O4, N2O4 decomposes into 2 NO2 molecules. So because the rate is equal, the amount of each stay constant. You've got to get that. So people love to choose 1. Okay? They're never going to be equal. What's equal in terms of quality would be how fast. So look at this. The rates of the forward are increasing. No, they're at equilibrium. And they're saying decreasing. So they're either going to mention that the amount of reactants and products stay constant, or the speed in the forward equals the speed in the reverse, or the rate of the forward. Now, if it's a phase change, they may just use the actual phase change. If a solid and liquid are in what we call phase equilibrium, okay, as fast as there is melting, there is refreezing. So let's say the rate of melting equals the rate of freezing. And that's the same thing as saying the rate of the forward equals the rate of the reverse. Any case, 21 is 2. On to number 22. Number 22, which phrase describes the effect of adding a catalyst to a chemical reaction in order to increase the reaction rate? Okay, so we know that a catalyst, like an enzyme, will speed up the rate of reaction, right? It'll make the reaction go fast. That's what reaction rate means. So what phrase describes another classic Regents chemistry question? So the way to think about this is thinking about a potential energy diagram. All right? Can't draw a straight line for some reason here, but I'll do my best. So this is potential energy. And if I draw an exothermic reaction, going high, going low, the pathway is how I get from high to low. It goes up and it comes down. And the reason why it goes up is because the molecules are going to start to collide and reach a pinnacle of repulsive forces called the activated complex. Now, the point I want to make here is, what are these different points of this? Well, the catalyst is going to change this pathway. You should know this arrow I'm drawing here is the activation energy. It's the energy needed to overcome the repulsive forces of 2 molecules. 2 molecules need to collide with enough energy, okay, and bond. You say, well, why does it go up? Well, because on the outside of atoms, you've got electrons. So electron clouds actually start repelling as 2 atoms come together. All right? And that's where the activation energy is. It's the energy needed to start the reaction. So if you have this nice understanding, if I wanted to use another analogy, is if I want to ride a slide, I got to get to the top of the slide. Okay, well, the energy needed to climb to the top is the activation energy, right? All right, so what does a catalyst do? It doesn't change the difference where we start and finish. That's a misnomer. What it does is it changes the pathway. It finds an alternative pathway, right? And so by lowering that height, okay, you're going to lower the activation energy. So catalysts lower the activation energy. Now you may say, well, how does that speed up the reaction? Well, if you think about it, if I use less energy to get to the top, there's more energy available for more rides in the same amount of time period. So we're looking for a different reaction pathway. Sometimes they say alternative, so different reaction pathway. All right, the same is not good here. And we want with a lower activation energy. And that's what choice 1 is. All right, we're going to change the pathway. We say pathway because, again, we're not going to change delta H. People think incorrectly. The difference where you start and finish is enthalpy, is the heat of reaction. In this case, it's going down, so it's a negative value. We're never going to change the enthalpy or the amount of heat released per mole, but we will change how fast it reacts. Okay, so in any case, 22 is 1. On to 23. Number 23, another classic question here, and you see this one a lot. Systems in nature tend to undergo changes toward what? Okay, well, things in nature tend to go toward lower energy for sure, right? For instance, I always think of a rock on top of a hill is going to go to the bottom of the hill. That's one thing I do understand, okay? So things in nature tend to go to lower energy, all right? A hot cup of coffee is eventually going to be cool if it's sitting in a cold room, right? So that's, of course, how heat flows. It's how diffusion works from high energy to low energy. Now, it also describes disorder. So disorder means things in nature tend to go from a ordered state to a disordered state. You never think about your room at home. Your room at home doesn't naturally get clean, right? It naturally becomes more disordered and cluttered. Your house, your room, your life. If you don't fight the universe, it becomes more cluttered. So things in nature move toward lower energy, just how it happens, okay? High energy wants to be given off and become lower energy. And things in nature will move toward a greater amount of disorder. Now, that doesn't mean that you can't work against these two things, but that means you're going to have to add energy, and that means you're non-spontaneous. So things in nature go from high energy to lower energy, okay? And of course, we move with greater disorder. And these two things are what make a spontaneous process. All right? And you think about a spontaneous process, you think about things that give us, let's say, energy like a battery without applying energy to it. You think of a non-spontaneous process, you think about like photosynthesis, right? Photosynthesis is moving toward higher energy because it's grabbing energy from the sun. And it's taking like CO2 out of the air and putting it together to make glucose. It's moving against, but it does so because you have to add a constant supply of energy. So without applying energy, things, okay, do this. They lose their energy and they have more disorder. Think of, unfortunately, nature. Everything in nature has to die and break down, and we think about decomposers helping that process alone. So 2 is the best answer here for number 23. On to number 24. Number 24, which element must be present in an organic compound? If you don't know this one yet, okay, I ask you to look at the 3 reference tables you learned in your organic unit. One was P, and table P lists the prefix of all carbon-based compounds by how many carbons you have. Meth was 1 carbon, eth was 2, okay, prop, like a propeller, was 3, and so forth. So that's the suffix for the longest continuous chain. In table Q, we put the ending, the suffix, right, the ane, ene, or ine, based upon bonds between carbons. If it's a single bond between carbons in a carbon chain, it ends in an ane. Right? If there's a double bond between carbons, it's an ene. Notice the theme here. We're constantly talking about carbons. And if there's a triple bond, it ends in ine. And if you go to table R, If you're from New England, it's R, because you don't say the R, I guess, so it's ah. Okay, it's a wicked nice state. But the point I'm trying to make here, if it's table R, we have a different functional groups on a carbon chain. So it's carbon. Things that are organic were past living things, and all living things are carbon-based. Carbohydrates, proteins, lipids, DNA, all carbon-based, right? So 24 is 1. Got to get this one down. They love to ask it. It's an easy gimme. Organic compounds are made from past living things. Past living things have carbon. Fossil fuels. Think of the word fossil. It was once living, and now it has carbons in it. The gasoline and those kind of things. 24 is 1. On to 25. Which compound is a saturated hydrocarbon? Now, I've seen this a lot, where they give you something that has more than just carbon and hydrogen. Hydrocarbons mean you just have carbons and hydrogens, no oxygen here. But this choice here doesn't have any oxygens or anything else, so that's easy, but I've seen questions that does. Any case, how do I know it's saturated? What does saturated mean? You have the maximum amount of hydrogens. Now we know carbon makes 4 bonds. So up to the right here, okay, if carbon makes 4 bonds, the only way to maximize the amount of H's is to have single bonds between the carbons. If you only have 1 bond, that opens up more bonds for the H's, right? Carbon makes 4 bonds because it is or has 4 valence electrons. So if you have a 2-carbon compound, you're going to have 6 H's that can maximally bond. Now, if I add a bond here, okay, if I add a bond here, then I have to do what? Take away, all right, a bond for the H's, right? And that would be an example of that would be C2H4. And if I add a bond here, I got to take another bond away. And that would be C2H2. So notice for a 2-carbon system, the number of H's is decreasing every time, this is a 2 here, I add another bond. And we would say that the ones that are decreasing, the ones in a different color, are unsaturated. Now there's a formula, if you don't want to draw these out and do this type of thing, and it's in table Q. Saturated, if you look at it, is the one that's C2H6 ethane. We're looking for an alkane, single bonds between the carbons that open up the possibility for the greatest amount of hydrogens. And the general formula given to you in table Q is CnH2n plus 2. All right, notice we figured out that this was saturated. So if I use the formula, okay, 2 C's, now double them, 4, and then add 2, that follows the formula. So who has the greatest number? Not these, because I kind of drew those. And so double the C's, that'd be 12. Add 2, that's 14. Choice 4 is an alkane because it fits the formula. Again, there's C6. 6 times 2 here, that's what that means. So 2 times the N is a number of C's, that'd be 12. And then add 2 more, so 2 times 6 is 12. Add 2, that gives you 14 H's. And if you're an alkane, you must have that, you must follow that formula. And if you're an alkane, you have single bonds between the carbons, which means you have more availability to have the greatest number of bonds with H's, and that would mean you're saturated. So I'm looking for an alkane with this general formula. Choice 4 is the answer. On to number 26. Number 26, which reaction occurs at the anode in an electrochemical cell? Okay, so we're dealing in a redox area, and it's really important to know where you are on the test. Since we're now, if you notice, we're in the high 20s, and we're finishing the first section at 30. And so at the end, we start from atomic structure, periodic table, bonding, some mathematics and chemistry, solubility, and now we're getting to redox, acid to base, and eventually nuclear. So know where you are. We're in the the redox area. But electrochemical cell means you have electricity, electrons. We're talking about either a battery, which is a voltaic cell or electrolytic cell that requires a battery to force oxidation. So anode, we have this kind of mnemonic that says anox. And at the anode, in a redox type of application called an electrochemical cell, we have oxidation occurring at the electrode always. So always there's oxidation, okay? I'm not loving this reaction part because oxidation doesn't happen really without reduction, but in electrochemical cells, they kind of separate them into an oxidation cell and a reduction cell, especially if it's a voltaic cell. But we're looking for oxidation here because we're looking for what occurs in a reduction oxidation reaction at the what? The electrode that is the anode. So if you've got a battery, you've got two metals, they're separated by two different containers. We have to have a salt bridge that allows ions to flow. More importantly, hey, electrons flow from who gets oxidized to who gets reduced. And so we're separating them. And so these metals here are the electrodes. These are the places where the redox occurs. Now the anode is the place where oxidation occurs, which means you're losing electrons by the mnemonic Leo, which means electrons flow from the anode to the cathode. The cathode is the place where reduction occurs by the mnemonic red cat. They could have easily asked what's happening at the cathode at an electrochemical cell, and you would say reduction, okay? And so that's the basics. Saponification is an organic reaction. We make soap, right? That's where we break glycerol with a strong base, we take a triglyceride, a big molecule, and break it up into 3 fat molecules, right? Esterification, this is an organic reaction, I should say, where we're going to take an alcohol and an organic acid to make an ester. All right? So choice 2 is the answer for 26, number 27. So number 27, which statement describes the two types of reactions that occur in an operating electrochemical cells? Electrochemical cells is a fancy word for the application of redox reactions that either produce energy, like a voltaic cell or a battery, or require energy to force the reaction together in an electrolytic cell, okay, or electrolysis. So we need to understand what non-spontaneous and spontaneous is. So a voltaic cell, which is a battery, okay, provides energy without any input. We take chemicals, we put them and arrange them in a certain way so that the chemical energy makes certainly electricity or electrical energy. So the battery or the voltaic cell provides us a battery without any input of energy, so it's spontaneous. Kind of like riding in a kayak, all right, and you are going with the current in the river or what have you. You don't really need to paddle. You'll move forward without having to add any energy. Now, in the electrolytic cell, which I write down here, that's electrolysis or electrolysis of fused salt or electroplating. They have the word electricity in it, and you'll see it electrolytic cells. These cells require a battery. You'll always see a battery in the diagram to make them occur. They'll take electricity and they'll make chemical reactions occur, but once the battery dies or you disconnect the battery, the electrolytic cell stops working. It's not a standalone device. So electrolytic cells are non-spontaneous. They do not work without an input of energy. It's kind of like, as I said before in my analogy, if you are riding a kayak and you are now trying to paddle against the current. You're only going to move forward as much as you paddle. You stop paddling, you stop moving, or in that case, you go backwards. So electrolytic cells are non-spontaneous. You've got to add energy to make them occur. Okay, and that's what non-spontaneity means. Another example of that would be, I think, a great example is photosynthesis. You need light to drive okay, the reactions in photosynthesis. Once there is no light, there is no photosynthesis. So it only works when there's an input of energy. So that being said, spontaneous reaction occurs in voltaic cells. And non-spontaneous reactions occurs in electrolytic cell. Think in terms of spontaneity, in terms of does it work without an input of energy? Don't think about activation energy. All reactions require activation, but we need a constant supply to make it work. Okay? Think of charging your phone. You stop charging when you disconnect it from a power source. It only starts charging when you connect it. So charging your phone or getting the battery back up, all right, is an electrolytic process. So number 27 is 3. On to 28. Which term describes an acid according to one acid-base theory? Now, if they're not going to name this other acid, it's normally going to be the Bronston-Lowry definition. What accepts as an acid is an H plus donor and a base and H acceptor. Case in point, if I have NH3, we know it's a base. It's written for you in table L, all right? It's listed as a base, yet it doesn't have a hydroxide. So if you put an acid next to it, like HCl, that's in table K, all right, what's going to happen is when these guys react, you're going to have something called NH4+. Now, what just happened? Well, what happened, of course, you're also going to have Cl negative too, all right? But the point I'm going to make is that an H+ was donated to the NH3. Acids give off H+. But specifically in the Bronston-Lowry definition, they donate them to something. So the NH3 gained an H, and it gained a +1 because of that. So it is going to be, so what describes an acid is that not only does it give it off, it's a donor. And if that confused you, just think about table K, right? The list of all the acids. You'll notice in all the acids listed, they throw the H in front to remind you of all the acids they give you, that H's are given off. Not really, it's not H's, it's H+, okay, also called protons, okay? So all the acids listed, with the exception of CO2, which it kind of gives its other form, they have the H's in table K. You can see that all acids are H+ givers because the H is in front. It wants to show you that it's giving them off, right? And so in this theory, it just does, it's a donating them. By the way, the other theory that has Arrhenius states that if you're an acid, hey, you just give off H+, you don't donate them. And the only thing positive in solution is the H+. So it's an easy way to think about acids are about H+. Also about H3O+, too, when water holds on to them. Okay, on to number 29. Number 29, which emission? Emission means that we're giving something off as energy or a particle, will be released, right? Which particle, I guess, is a type of particle that's released, okay, from an unstable nucleus of iron 53. So what kind of particle, okay, is given off by an unstable nucleus? Well, you should know that we're in the nuclear chemistry area of this test. The last part of the 1 through 30, okay, usually is a nuclear area. And you should know that there's that nuclear chemistry, it's really physics, but nuclear chemistry is we have an unstable nucleus. It's about the nuclei, nothing about the electron. It is high energy. There's something wrong. It might have too many protons, too many neutrons, or too less neutrons. Something is not quite right. So things with high energy are unstable, and they give off particles, like the choices here, to become more stable, to improve their nucleus. I say improve because if there's too many neutrons, they're going to give a particle to lower their neutrons. If there's too less neutrons, they're going to give off a particle that increases their neutron ratio. And if they have too many protons, they're going to what? Give off a particle that decreases their proton number. You should understand an unstable nucleus has the wrong number of things, okay, subatomic particles inside the nucleus. So what does it give off? Well, you should not know this off the top of your head. So there's a place to look to see what kind of particle iron 53 gives off, and that would be table N. So let's go there. So table N gives me the types of selected radioisotopes, meaning that not every isotope, which you know is the same number of protons, different number of neutrons, okay, that are radioactive, right? So if we look at this exact isotope or this nuclide of iron 53 that was in the problem, they want to know what kind of particle is emitted, so what kind of emission. And so I look at the decay mode, and in the decay mode I see it's a B plus particle. That's the particle it gives off to correct its unstable nucleus. All right. Now, if they didn't have a B plus there, okay, so we're going to have to know what the B plus is, and so we're going to go to table O now to see what that is. So I'm at table O, and I'm trying to figure out what that particle is, and a B plus is a positron. So iron 56 decays into a more stable nucleus by giving off a beta, or in this case a positron. It looks like a beta particle, but it's a positive beta particle or positive electron. We call it a positron. So back to the question. So 29 is 3. And essentially this was reading right off the reference table. You just have to know where to look and when it's a reference table question. Okay, so table N, just reading right off and knowing, understanding what that means. So any case, number 30. What is the potential risk associated with radioactive isotopes? Okay, well, the risk is, okay, not curing of diseases. That's a positive, okay, part of radioactive isotopes, right? Industrial measurements. We can measure things with radioactive isotopes. That's a positive, not a risk. And tracing chemical processes by putting a radioactive tracer to see how the reaction is proceeding. So these 2, 3, and 4 are not risks. They're actually positive, okay, components of radioactive isotopes. The one is biological exposure. When we expose, okay, our biology to radioisotopes, they could mutate our DNA and cause cancer or radiation poisoning or sickness, right? So living organisms can only take a certain amount of this type of radiation that's emitted when unstable nuclei become stable, or the particles listed in the choices in number 29. So the radioactivity we talk about, all right, is a potential danger to living things. Certainly, there were more people, unfortunately, that died when we dropped atomic bombs in Hiroshima and Nagasaki. More people actually died from the radiation sickness and poisoning than they actually did from the explosion. All right, so something to consider. So number 30 is number 1. Now we just completed questions 1 through 30, and this is part A, and these are the more faster, and I say faster, I mean that there's a definite answer to get to. Normally these questions are single step type of concept questions, where 31 to 50 are more advanced in their sometimes 2 or 3 steps, or they require a deeper thinking process or concept involved. So I like to think that questions 31 through 50, although there's still multiple choice, are much like your free response part of the test, okay, the part B2 and the C, and that's a good place to go. So we're going to go on to now 31. Number 31, which electron configuration represents electrons of phosphorus atom in an excited state? These are the most important terms. So I always tell my students, you say atom, I say neutral, atom, neutral. So atoms are always electrically neutral, and that's because the positives equal the negatives, which means the protons equal the electrons. So if I have a phosphorus atom and I go to the reference table, I will see that phosphorus is atomic number 15. The biggest, baddest, boldest number is the number of protons that identifies the element, which means it's going to have 15 electrons. So if I'm going to pick any choices, it's got to add up to 15 electrons. Now, if you also notice in your reference table, they give you 2-8-5 as the electron configuration. That's 2 electrons in the first shell, 8 in the second, and 5 in the outermost. Now, when they give you an electron configuration in the the reference table, in this case the periodic table, they give you something called the ground state. The ground state is the lowest energy position, okay, the ground state. And that means electrons are going to fill lower energy positions first before they fill higher energy positions. Electron shells that are farther away, think of the nucleus in front here, it's positive. Electron shells that are farther away are higher energy. That's why we said the highest energy ones are the valence, the outermost. So they give you the electron configuration in the ground state going exactly in order. Now, the excited state means that somehow this atom absorbed energy, and electrons in lower energy states jumped to a higher energy state, leaving an electron configuration going out of order. If you notice, 2-8-5 is the ground state configuration that's given to you. That's not the correct answer. And if you notice, choice 2 is 2-8-6. That's also ground state, but that's not the right number of electrons. That would be for sulfur, right? We have to equal to 15, right? And so now we're left with 2-7-6. Now these are going out of order. You can't put electrons in the third shell until you have 8. So this is telling us that an electron jumped from the second to the third. Same thing for 4. So who is going out of order, 3 and 4, but still adds up to 15? We didn't say this was an ion. We said it was an atom. An ion means you lost or gained an electron. So it still has to add up to 15. So clearly, number 3 is the choice here because 7 plus 6 is 13 plus 2 is 15. And you can see if one electron from the second jumped to the third, okay, this would go to a 7, 2-7, and now this would go up to a 6. All right? So in any case, 31 is choice 3. So you can see that this question, not only did you have to figure out the excited state, you had to do it for an atom. So you can see that there's more than one concept in this question. That's why these are the part 2B questions. In any case, on to 31. Number 32. A 26.7 gram sample of which element has a volume of 3.0 cubic centimeters at room temperature? Well, we're trying to identify the element based upon mass or volume. Never going to work. I can have as much volume as I want or mass. I'm going to need something called an intensive physical property. And one of those properties is density. So you had to recognize that if I have the mass and I have the volume, I can solve for the density. So let's do that, because once I have the density, I can hopefully find a place to look that gives me the density values, which is table S. So you probably did this lab, so 26.7 grams divide by 3.0 cubic centimeter. Cubic centimeter is this. Don't worry about that. It's the same size as a milliliter. Now, when I put this in my calculator and I divide by 3, 26.7 divide by 3, 26.7 divide by 3, I get a density equal to 8.9 grams per centimeter cubed. That's the first part of this problem. Remember, these problems are generally 2 parts. So I've got to find a place where I can match this intensive physical property of density to a table that will tell me which element, and that is table S. It's the most underutilized table. Okay, so let's go to table S and look for these densities. So in table S, we've got all this information people don't realize a lot of times, but it also includes density. Okay, so I'm looking for 8.9, okay, or I'm sorry, 8.9 grams per centimeters cubed. That's what we just actually solved for, so it's in the same unit. So they're trying to match the value. Okay, so if I scroll down, and I'm just going to look for 8.9, and I found it. Okay, I can see the 8.9 toward the bottom here is the density, and my gosh, it's nickel. Okay, so I basically identified nickel based on the density. So choice 4 is the answer. You can see there's definitely 2 parts to this. Okay, so on to number 33. 33, which element is a nonmetal and a solid at STP. All right. Well, I should know my nonmetals are above the staircase. Okay? And lead is not a metal. I'm sorry, it's not a nonmetal, it's a metal. Okay? And I'll explain that. And sodium is also a metal. So now I have to figure out. Now, let's go to the periodic table for a second just to briefly talk about how I knew that if you're down on this topic. So on the periodic table, you've got this darkened staircase here. And that includes boron is on it, silicon is on it, arsenic is on it, tellurium is on it, acetine is on it. Okay, I know what's going on there. My pen went astray here. Okay, now also germanium is involved and antimony. So all of these elements here, okay, they're on the staircase. In the case of germanium Sp, they're close to it, those two. Those are metalloids. Okay, they have properties of both metals and nonmetals. You should be aware that everything above the staircase or to the right in this general vicinity, okay, are nonmetals. All right, and they tend to gain electrons. That's why you see negative oxidation states for most of them. Now, very important, your metals, of course, are to the left. So if you notice we had lead is below or to the left of the staircase, that's a metal. Sodium, which you don't see in this picture, is way over in row 3, period 3, okay, group 1, and that's off to the left. All right, for the same reasoning, it is a metal. So now we're left with nitrogen and sulfur. Okay, so how do I detect who is a solid here? Well, I might know that at room temperature, nitrogen is a gas because approximately 80% of the air is made of nitrogen. So that leaves me with sulfur. Sulfur is a component of gunpowder. It's a solid. Now, you may not know those basics. So if you're not sure and you need to know who the solid or gas is, the best place to do this is table S. Again, using table S. Let's go there. So it's between nitrogen and sulfur because they're the only nonmetals in my choices. But who is a solid? Well, if I check out nitrogen, I'm going to go to the melting point. Okay? And if you think about melting point, we're going to compare it. The problem set at STP, standard temperature and pressure. So standard temperature is 273. This is telling me that it melts at 63. Well, standard temperature is 273. Heck, that's telling me that nitrogen has already melted, right? But here, check this out. Boiling point is 77. That means it boils at 77. Well, wait a minute. If we're at 273, it already boiled. To get to 273, you got to pass 77. So this tells me I'm a gas. So that's how you do that, right? Now, sulfur, at its melting point is 388. Well, at STP, we're at 273, which means we're below the melting point, which means it hasn't melted yet, and sulfur is a solid. So that's how I'm doing it. Again, at room temperature, or at least in this case, I'm at STP 273. If the melting point is above my current temperature, it didn't melt yet. So it must be a solid, and that's why the choice is sulfur. So number 33 is 4. On to 34. What is the molecular formula for this compound? Okay, so this compound is giving me a structural formula. It shows me the structure. The molecular formula is just a formula that tells me exactly how many of each type of atom I have. So let's put the C in front because in organic compounds you have to have carbon. So we got 1, 2, 3, 4 carbons. So I put C4. Okay, you can see that eliminates choice 1 and 2. Then I'm going to have how many H's? Well, I have 3 plus 2 is 5 plus 3 is H. I'm 8. Okay, so H is 8. Okay, and then I have O. All right, 2 oxygens. OO. All right, so O2. All right, so you can see C4H8O2 is the molecular. That's the exact formula. This it tells us exactly how many of each type of atom. It doesn't give us any indication of how they're bonded. It's not a structural formula, and it's not an empirical formula. They could have asked for the empirical, and that'd be the lowest ratio. Let's do it for fun. That'd be C2H4, and O. That's the lowest ratio. That's ugly. So that'd be C2H4, and that'd be O. All right? So in any case, that would be if it was asking for the empirical. But they just wanted how many of each. That's the molecular. Okay? And that is choice 4. On to 35. Number 35. A substance conducts electricity in a liquid phase, but not in a solid phase. Boy, this is kind of like straight definition. Okay? It is an ionic compound. Now, the answer needs to understand, when you conduct electricity, you are doing two things, or you have two abilities, or one of the two abilities. One of them is you have free moving electrons. And so we know that metals like copper and many metals bond to themselves. This would be a formula, it would be metallic. They can conduct electricity very well because they have a sea of mobile electrons that can move throughout the crystal. But this said conducts not in a solid phase. Metallic compounds like copper conduct in all phases if you can conduct. All right, so solid and liquid. So this conducts as a solid. So that's why this isn't the answer. Molecular compounds is a fancy word for covalent. And these guys do not have mobile electrons. And they also don't have the other form that allows electrical conductivity, and that is free ions to move around. So molecular compounds do not break apart into ions, with the exception of acids, right? Acids, bases, and salts are what we call electrolytes. For generally speaking, these guys are terrible conductors because they hold on to electrons tightly. So they're not going to usually conduct in any phase. All right, and by the way, molecular and covalent mean the same thing. Covalent compounds make molecules. Ionic compounds make what? Crystal lattices of positive and negative ions. You've got to think about ionic compounds in terms of their properties based upon the crystals they make, right? So ionic compounds cannot conduct in the solid phase. If I draw a crystal of an ionic compound, these ions aren't free to move if they're in a regular repeating arrangement as a crystal. All right, so crystals, or we say solids, are in this arrangement. So ionic compounds, the ions aren't free. But if you heat them and make them into a liquid of ions, now the ions are free. Okay. Also, they'll conduct in an aqueous solution if they're soluble, because they'll break apart into ions within the water. Okay. So classic question that talks about ionic compounds, choice 2, they conduct not as a solid because the ions aren't free, but they will conduct in a liquid or aqueous. 35 is 2. On to 36. Number 36. A student measured the melting point of a sample of gallium to be 309. Based on table S, they're being real nice to tell you it's there. Which numerical setup can be used to calculate students' percent error? So if the student measured 309, hey, that's the measured. Now, the percent error formula is given to you in table T. And it's measured minus the accepted. This accepted is in some form of publication. In our example, it's in a reference table. And table T says measured minus accepted divided by the accepted. And you times that by 100. This is right from table T. No reason not to know this. This is percent error. Okay? Now, what are they giving me? They're giving me the student's measurement. Well, the student measurement, okay, is 309. That's the measured value. So that's 309. And that goes in front. And you can see for a second here that we can get rid of 3 and 4 because we're not subtracting the measured minus accepted as it should be in a percent error formula given to you in table T if you don't know. Okay, now the accepted value has to be something we get from table S. So 39 minus some number, that's different. Notice, okay, they have 303 on the bottom. Look at choice 1 here. They have 309 minus 303 over 303. So this must be some number that could be from table S. Now we're going to check that in a second, but look at choice 2. 309 minus 303, that could be the different number, but notice they're dividing it by the what? The measured value. We divide by the accepted value. So if you look very carefully, I can eliminate choice 2 because I should be dividing by some number other than 309. I should be dividing by the number posted in table S. Okay? And for speed purposes, you don't, if you look up the melting point on table S, you will get 303. Okay? But you didn't really have to if you know the formula. And again, if you didn't know the formula percent error, table T is your friend here. All right? So for all those reasons, 1 is the answer, because you're going to be dividing by not by the measured, by the other number. And of course, that makes this incorrect, and therefore 1 is the answer. And if you want to go to table S, stop my video and go, and you'll see that the actual melting point of gallium is 303. Number 1 is your answer. On to 37. Number 37, which bond is most polar? This is not asking which molecule is polar. We're talking about the bond. And polar means there's differences. Why is there differences? Because in a bond like this, we're talking about a covalent bond. And you should know covalent bond is sharing. Now, if I have an O and I have an H and they're sharing electrons, okay? If they are the most polar, they're going to share the most unequally, right? So what I'm going to do is draw a box here with a different color, okay? So I'm going to draw a little box here the best I can. And these where the 2 electrons can fit. Now, if they're polar, just like if I have a polar personality, I have what differences? I'm moody one day and some days I'm not. Hopefully I'm not. But in any case, the pair of electrons is a bond. We should know that from covalent bonding. If it's the most polar, then we're going to have the greatest differences in how they're sharing. It's going to be sharing the most unequal sharing. Most unequal. And why would that be the most unequal if it's polar? It'd be the most unequal because there's the greatest difference in electronegativity. Electronegativity is the attraction for electrons. So if O is so much more attracted to electrons than S, it's going to pull this pair closer. It's going to make this side of the bond more negative and this side of the bond a little positive. And that's how we get the polarity. We pull those electrons. We share them most unequally. Now, how do I know it's OH and not SH, SEH, or TE? Well, I can go to the periodic table, the reference table, and I can look at table S, and I can look up every single one of these and subtract. Okay? Or I can understand my trends. Since I'm bonding with H, all I got to do is pick out of these 4 who is the most electronegative. Now, it's very interesting that all of these elements are in the same column. And you should know when you go down a column, the atomic radius gets bigger because you're putting electrons in a shell that's farther away. And what is electronegativity? Electronegativity is a word that describes the attraction for electrons. So electronegativity is about the attraction for electrons. If your electrons are farther away in these shells than the nucleus who's positive in the middle, it's hard to attract them. So your electronegativity drops as you get bigger. So since oxygen's above the rest of these, this has the greatest electronegativity, and thus this would have the greatest difference. But if you don't trust that I'm saying is correct and you don't like using the trends, you certainly can go to table S. I keep talking about the most underutilized table and measure the what? Electronegativity of these 4 elements. And you could see that O has the greatest electronegativity. And if you wanted to, you can look up the H and subtract them. And you'll see that the greatest difference is choice 1. 37 is 1. On to number 38. Number 38. What is the amount of heat required to melt 43 grams of solid magnesium oxide at its melting point? They're screaming to you that we are at a phase change. And you should know from this point that at a phase change, there is no temperature change. And since they're asking for the amount of heat, I need one of 3 thermal equations that is listed in table T. So to measure heat, I have 3 equations. Q is joules. Now you notice one of them has a change in temperature. But if you're at a phase change, you don't. And if you forget that, if I do a little heating and cooling curve here, this is a solid heating up. Oh, it's melting. Then it becomes a liquid. Oh, then it's a vaporizing phase change, and it's a gas. So you should be aware that the phase changes are where the temperature stays constant. So you can't use this formula. Fusion is a word for melting. So I use mass times the heat of fusion. If I was talking about a phase change where a liquid was going to a gas, vaporization or boiling, I would use this one. But now my formula is Q equals mass times the heat of fusion. You need the mass of your compound and the heat of fusion. If it was water, in table B, they give you the heat of fusion, but this is not water. And they gave you the heat of fusion of aluminum. Let's go do it. So I now know that the heat, or the Q in joules, is equal to the mass times the heat of fusion. So the mass is 43 grams. And the heat of fusion, they had to give this to me because it was not water, okay, was 1.9 times 10 to the 3. If you don't like the scientific values, hey, just make it into a regular number. So that would be 3 more, Move this decimal plate, 1, 2, 3. 1, 2, 3. It's 1900. Or just type it into your calculator, okay? So all I'm doing is multiplying the heat of fusion times the grams. Now, the heat of fusion is in joule per grams, so the joule will cancel. The grams will cancel and give you joules. But in any case, it's 43 times 1900. Okay, so party people, let's do it. 43 times 1900. And I get a raw number that's unrounded, and then I'm asking for sig figs here, of 81700. So 81700 joules. So 81,700. And if you notice, the number that's closest is choice 3, right? That 8.2 times 10 to the 4, right? 1, 2, 3, 4. So that's 8.17 times 10 to the 4. And they just rounded to 8.2 there. So 3 is your answer. Straight plug and chug in. Just you needed to know that you needed to use this thermal equation. How do you know? Phase change. Phase change doesn't have what? Temperature changes, okay? And you need a constant. This wasn't water, they gave you one. On to number 39. So number 39, they give you a picture of a apparatus, a setup, and they're telling us that there's salt water. That's a solution. It's aqueous, homogeneous. And they're saying that somehow through this apparatus, water is dropping out. Okay. Now, it's a little bit confusing because they're pumping water in and then water's coming out. And to explain this, they're pumping cold water. This is a tube within a tube. There's a circular tube. If I draw a cross section, this outer tube is filled with cold water that's pumped into this inner tube. It never touches the inside, so it keeps the tube cold. And as we add the hot plate, we add heat. The water evaporates away from the salt water. It's a gas. It collects in this tube, in the inside of the tube. Because of the cold temperature, the gas condenses into a liquid, and then it drips into this container. So we're separating the water from the salt water, okay, by evaporating off the water. You could say this is evaporation, okay? But this is also an apparatus called distillation. Okay, and distillation normally is when we separate liquids based upon their different boiling points, right? So if we had two different liquids, okay, like alcohol and water, that do this when they are distilling out alcohol from the mash when they make whiskey or some kind of other alcohol. They want to separate the alcohol. We know the water and alcohol have two different boiling points, and the alcohol boils first. Okay, because in a mixture, the components of a mixture retain their individual properties. So this is a classic case of separating a mixture based upon the mixture retaining its individual properties. So where water still boils at 100 or close to that, and it will do so and be collected in the salt we stayed behind. It's not filtration. We're not filtering off the salt water, nor could you ever, right? You can't filter salt water away from the water if it's dissolved. Chromatography is how we separate compounds based upon solubility, right? If you remember, chromatography is we have some sort of plate. We spot it with a mixture. We let a solvent run up the plate, and we give these spots, which are the mixtures, a choice to either stay with the more polar silicate background or the more non-polar solvent front, and these spots will separate based upon their difference in solubility. Electrolysis is that setup where you need a battery to make a redox reaction. It's a non-spontaneous process. So this is distillation number 2. On to number 40. Number 40. Solid aluminum has a specific heat of 0.9. And they want to know how many joules of heat are absorbed to raise the temperature of 24 grams of aluminum from 300 Kelvin to 350. So they have a change in temperature. And if you look at table S, okay, if you look at table S, we'll see that there's only one formula that has a change in temperature, okay, when they're solving for energy. And it's that one. These other two are when you have a phase change and temperature doesn't change. So here we're going to use Q equals MC change of T. All right, so I'm going to use that formula. All right, and here I go. So Q is equal to MC change in T. Now, what's different about this problem is we're using aluminum, not water. So the specific heat will not be 4.18. It will be what is given to you. Understand these Q formulas is always the same thing. Mass of the aluminum, which is 24. Specific heat of aluminum, which is 0.90 joule per gram per Kelvin, times the temperature change. Well, 350 minus 300, that's just going to be 50 Kelvin. And it's a plug and chug. So far in this test, all we've done is find the right formula and we plug. We don't put the water in. The Q formula is always the same. So when I put this into my handy dandy calculator, 24 times 0.9, low specific heat for metals, times 50, I get, all right, an answer, if I can see my calculator, 1080 joules. And 1080 joules will round, if you need 2 sig figs, and I'm looking for 2 in this answer, to 1100 joules. That's the closest answer, right? So that is your answer there, choice 3. So that's just plugging in the thermal equation that you need to change the temperature. On to 41. Number 41, okay? Based on table G, so we're going to have to go there. Which solid sample at 100 can produce a solution equilibrium? Solution equilibrium. That, my friend, okay, is something special. Let's talk about that because people don't or forget what that is. If you've got equilibrium, you got the rate of the forward equals the rate of the reverse. But here's what solution equilibrium means. We have some solid in equilibrium, in this case, since they're all ionic, with their ions. What that means is if I have a beaker here, or a container, I'm going to have some solid. I'm going to have, of course, a solution. And the solid is going to dissolve as into ions, plus a negative, as fast as the ions reform the solid and make a precipitate. So the amount of solid ions stay constant. So what they're really describing here is that I'm going to have some amount of undissolved solute, and then, this is really important, this is where people forget, you're also going to have a saturated solution here. To have what we call solution equilibrium, this has to be saturated. And the best way to explain this is that if I have a room that 100 people can fit in and there's 2 doors, well, I'm going to keep dissolving or keep adding people until I get 100. Once I reach 100, if 1 comes in, 1 has to come out. There's your equilibrium. So we have to be saturated, and we have to have more, more solid that can be dissolved. So what they're describing in table G is something that's above the line, right? So we have in table G these solubility curves. I'm trying to get a different color here. That wasn't successful. And so if you got a solubility curve, this is temperature, this is the amount of grams of the substance. And so if I have a certain amount of grams of substance, I've got to be above the line. I've got to have enough of it that's above the line. Now why? Whatever is above the line is called supersaturated, and that's how much will not dissolve. And whatever is on the line and below would be totally saturated. So on the line. So we're going to have a saturated solution, right, because we're on that line. And because we're above it, we're going to have some solid. So we're looking for a supersaturated solution that's going to give me some solid that's undissolved. Anything above the line can't dissolve. And then what's remaining is a saturated solution underneath it. So what they're really saying to you is in table G, which one is supersaturated? So we need to go there to find out. So here we are at table G. We always have to make sure that we're in 100 grams of water here. But if you look at the choice 3, which is 45 grams of KCl, so 45 grams of KCl at 40 would be approximately here. And the solubility curve of KCl is below it, right? So there's KCl. So we're above the line, which is supersaturated, which means this amount above the line is going to be solid, and what remains is 39 grams that are saturated, and that's going to give you solution equilibrium. You need a saturated solution, but you also need a solid. So that's why you have to be above the line. It's the only choice that does that, and that's why the answer is KCl. All right, so back to the test. It's 45 grams of KCl at 40. Notice 100 grams of water. Okay, so choice 3 is the answer. On to number 42. Number 42, given the equation representing a system in equilibrium, which change favors the forward reaction? What they're really saying is, what's going to make the reaction shift to the right? It's in equilibrium. So the rate of the forward equals the rate of the reverse. We want to get it out of equilibrium for a little bit. Okay? And what we do is, we add something called stress. It's Le Chatelier's principle question. And when I do it, I do stress is what people do, and the response is what the reaction does to regain the balance. The regaining the balance means re-achieving equilibrium. So if I push on you, you're going to fall over unless you push back opposite. The reaction's always going to push back opposite and do the opposite. So let's go through these stress. All of these are stressors that are going to force it to go to the right. So if I increase O2, that's my stress. The reaction is going to look to lower O2 to regain its balance. So if I increase O2, it's going to shift to the right to use up SO2, O2, and make more of this. So actually I just ran into the right answer, right? Increasing O2, the reaction is going to look to make lower O2 by shifting to the right. Okay? So that actually is the right answer. But let's go through the other choices to see if it makes sense to you, trying to teach this to you. Increasing the temperature. Notice where the energy is. So if I increase the temperature, the reaction is going to shift to lower the temperature. The only way to lower the temperature is to use up the energy, which means we need to shift in the reverse to use up the energy. They wanted to go forward more, so that would not be an answer. Anytime they mention pressure, so decrease the pressure, you count moles of gas. Well, on this side, there's 3 moles of gas, right? 2 plus 1. On this side, there's 2. If you decrease the pressure, the reaction is going to respond and do the opposite by making more pressure. And we should know making more pressure means you're going to shift to the side with more gas. More gas particles leads to more collisions, more pressure. They want to shift to the right, so that doesn't do it. Decreasing SO2. Hey, what's that going to do? If you decrease SO2, the reaction is going to shift to make more of it. It needs to make more of SO2, and you would need to shift to the left. So it's shifting to the right. So the only one that will shift to the right to respond in a way to regain its balance and undo in the opposite way would be choice 1. 42 is 1. On to 43. Number 43. When ice melts, its entropy does what? Well, entropy is a measure of disorder or randomness. So a solid you should recognize has a regular repeating 3D arrangement that keeps going in all directions. And if it melts, it's going to come out of that order and become more disordered. Liquid molecules have more range of motion. Solids only do what? Wiggle in their fixed position. So entropy increases. It's got nothing to do with the energy, at least the motion energy in this course. I say that because there is some tie to it. But the entropy increases because the particle arrangement is more random. Liquids have a greater degree of freedom. They can move, and they can spin. They don't have to stay and wiggle in their fixed position. So liquids have more randomness than solids, and gases have even more randomness as they can fly out of the beaker. Okay, so 43 is 3. On to 44. Number 44. At STP, propanol and propanone have different chemical properties due to their different what? Well, if you're not sure, okay, they love to talk about isomers. And isomers have the same number and types of atoms, same molecular formula, but different structure. Structure is king. You change the structure, you change the properties. So if they're talking about chemical properties, and they're talking about what? Different functional groups, because if you go to table R, al is an aldehyde, one is a ketone. And the reason why ketones and aldehydes are a class of compounds that are different, they have different chemical properties because the functional group has a different structural formula. But if you look even careful, prop is 3 carbons. Ane means there's single bonds. Take the E away and you have an al, and al means you have a carbon double bonded to an O at the end. Fill it in with an H, and this is propanol. I'm using table R as my friend. And these are all H's here, so it's C3, H1, 2, 3, 4, 5, 6, H6, O. Let's do propanone. Prop is 3 carbons again, ane is single bond. Now one is a ketone. Ketones have a carbon double bond in the middle. Carbon must make 4 bonds, so this carbon hasn't any H's left. This has what? 3 H's. And if you do the molecular formula, C3, H6, O. They both have the same number of stuff, but a different structure. They're talking about isomers. And isomers will have the same molecular masses because they have the same number and type of atoms, so their atomic masses will all add up to the same number. And they all have the lowest ratio because their molecular formulas are the same. And they'll have the same percent compositions. What's different is their structure. Functional groups have different structures. Different structure, different chemical properties. That's what they're after. Choice 4. On to 45. Number 45. Given this compound, an organic compound, it's carbon-based. What is the IUPAC? Oh my gosh, what's IUPAC? It's just the naming system that you learned. Don't get all crazy. And the naming system is find the longest continuous chain of carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 6. The longest continuous chain of carbons is right here. So if you go to table P, you'll see the longest continuous chain starts with a hex. And because there's single bonds between the carbons, you go to table Q, it's an ane. That's how I build that. Now, we have two attaching groups. They're the same group, but they attach differently. This is a one-carbon group. This is a one-carbon group. If you go to table P, that's a meth. If it's an attaching group, we add a YL. So these are two methyl groups, and they're attaching the longest continuous chain. And part of the IUPAC naming system is that we put the attaching groups on the lowest number carbon possible. So we could count this 1, 2, 3, 4, 5, or if I count the other way, this would be carbon 1, carbon 2, and carbon 3. It'll be 2, 3. So the attaching groups have to have the lowest number. The numbers are there to tell you where the methyl groups are. Notice the die that tells you have two of the same. But the 2, 3 means on the second carbon, I've got a methyl group. On the third carbon, I've got another methyl group. We don't use the bigger numbers. So this is the answer. By the rules of the IUPAC naming system of naming organic compounds, attaching groups have to have the lowest numbers possible. That's why 4,5-dimethyl doesn't work. So 45 is choice 2. On to 46. Number 46, given this formula, they want to know what's classified. What class of compounds? So it's an organic compound, carbon-based. We have three tables, P, S, and R. R is going to tell you the functional groups and give you examples. Okay? So here's what I know. I know that this is usually the R, the rest of the organic compound. So that's an R. Now it's bonded to a carbon that's double bonded to an O. That's bonded to an N, H2. And it's at the end. All right, so I'm going to have to look in table R and see which one of these four match up. Let's go there. So if you notice, we've got our table R in all of its glory. And we have this R here, the rest organic compound. We have a carbon double bonded to an O, and then we have an N. Now this little R prime means that we can continue this, okay, and with an H or possibly a C. But you notice, look at the example they give us. They give this thing at the end. This is exactly what we have. The rest of this could be different, right? That R there could be any hydrocarbon. But the class of compounds that matches that is an amide. Now, it's very close to an amine. Amines just have a nitrogen bonded to carbons. You have to have a nitrogen bonded to a carbon double bonded to an O there. That's that formula here, that general formula that kind of gives it away. All right, so it's an amide. All you're doing is matching with table R. Silly to get that wrong. But if you don't know where to look, it becomes a very hard problem. It is a table R problem. Choice 1. Number 47, who is an electrolyte? Okay. An electrolyte is something that conducts electricity in a solution. To conduct electricity in a solution, I'm going to say it once, you have to have free ions, ions that are free to move, okay, within the solution. Well, who produces free ions? Three things. Number 1, acids. They break apart into H pluses. Their conjugate bases are negative, but H pluses. 2, bases. Bases become charged when they accept a proton or dissociate hydroxides. And 3, ionic compounds or salts, right? Soluble ionic compounds break apart into ions. So who is an acid, base, or a salt? Well, if you don't know, these are molecular compounds. They do not break apart into ions. But this is a molecular compound. It's an exception. It's an acid. And if you didn't know it's an acid, the H in front is telling you, or you can go to table K, it's listed. And so it's an acid. Acids are great electrolytes. They have tremendous amount of free ions to conduct a charge through a solution. Number 47 is 2. On to 48. Number 48. An indicator is added to an aqueous solution with a pH value of 5.6. Which indicator is paired with the observed color? This is another right from your reference tables. Table good, table M, is going to tell you. So we got to figure out which one is which. So we've got to go to figure out what the observed color change based upon the chemical indicators. So off we go to table M. Here we are at table M, and the acid value, or the pH was 5.6. So if we go through our choices, methyl orange says at 4.4 and greater, it becomes yellow. And 3.1 and lower, it's red. Since they gave us a pH of 5.6, hey, that's above 4.4, so that's yellow. If you look at your choices, they said methyl orange is yellow, and that's your answer. Okay, the other three choices give you the incorrect color change. So the pH was greater than 5.6. If you look very carefully, if I'm 5.6, there's no way phenolphthalein can be pink. You have to be greater than 9, so that doesn't make any sense. Brome cresol green, okay, is going to be blue, okay? It's not yellow because it's 5.6, so anything 5.4 and higher will be blue. And thymol blue, they said, is blue, but that's blue when it's 9.6 and greater. Hey, it's between here. Thymol blue would actually be green in between these two colors, right? 5.6. I'm sorry, it would be yellow, my bad. It would be less than 8.0. Okay, sorry, so it would be yellow, all right? So in any case, methyl orange is the winner. And we've got methyl orange, choice 1. On to 49. Okay, so a solution of 49, I got to circle it, right? So number 49. So a solution has a pH value of 2. So solution A has a pH value equal to 2. And that's solution A. Solution B has a pH value of 4. How many times greater is the hydronium ion? Now the hydronium ion, you need to know, is H3O+. It is synonymous. It's the same as an H+, which means they all come from acids. So that means if we have a more acidic solution, the concentration of both of these, or one of them, they're really the same thing, increases, and we're getting more acidic. So how many times greater is the hydronium ion in solution A? Now, if you don't know, okay, do alphabet A to B. Acidity has a low pH, so there's a 7. So as we drop our pH, we get more acidic. As we increase, become more basic. So you should know that the hydronium ion concentration, of course, is increasing, okay, or is greater in A because the pH is lower. How much greater? Well, some people say it's 2 times greater because it's a movement of 2 pH values. That would be wrong. Okay? It moves by the power of 10, or 10 times. And the reason for that, okay, real quickly, is if you've got a pH of 2, the concentration, the molarity of the H3O+, or the H+, is 1 times 10 to the negative 2. The concentration of pH 4 is 1 times 10 to the negative 4. Now, if I give you these numbers, this will be 0.01. This will be 0.0001. So this is 100th, and this is a, what, 10,000th. They differ by what? 2 zeros. So you can probably see that this number, if I times this number by 100, I get the same number. So the point I'm trying to say is we're changing exponents. Base 10. All right? So we get the pH by taking the positive value. So a pH of 2, okay, is actually 10 to the 2 bigger than a pH of 4. And 10 to the 2, if you had the math, is 100. If you don't like any of this, every single change, unit change of a pH changes 10 times. So if I go from let's go from 4 to 3. Hey, that changes 1 unit in pH, so that's 10 times. If I go from 4 to 2, changing that's another 10 times. 10 times 10 is what? 100 times. And if I go from 4 to 1, we know we're going down 3, but take 10 times 10 times 10, that's 1,000. Okay, so every single change of the pH scale is another 0 change in actual concentration or times change. So 4 going to 2 is increasing the acidity because we're getting more acidic, okay, 100 times. And that is choice 3. They love that question. Number 50. Which net change occurs in both nuclear fission, that's splitting a big nucleus into smaller nuclei by absorbing little slow-moving neutrons, splitting the atom, and nuclear fusion, which is light nuclei like hydrogens coming together to make helium, fusing together. Okay? So what net change occurs? Energy is converted to mass. Small nuclei forms a larger nucleus for fusion. Large nucleus splits into smaller for fission, but we're using both. And you need to know that the tremendous amount of energy that nuclear equations give off is due to a little bit of mass that goes missing in all nuclear reactions. All nuclear reactions have a tiny bit of mass that's missing. And if we use Einstein's famous equation, E equals mc squared, if you take that little bit of mass that's missing and times it by a big number, the speed of light squared becomes even bigger, you get a lot of energy. So it's called mass defect. And you need to know that nuclear, not chemical, okay, convert a little bit of mass to energy. All nuclear equations do that, okay, or nuclear reactions. It's not really chemistry, it's physics. So 50 is 1. And that concludes the multiple choice section, okay, and we're going to go on to, in the next video that I'll produce, the part 2, or at least the free response section of this test.